Imagine a weather model that doesn't just predict the forecast. It understands the uncertainty in every storm, every gust, every drop of rain. One that runs faster than real time, yet delivers kilometer-scale precision with full probabilistic depth. This isn't science fiction. It's Bris CRPS-FFT, the first high-resolution, data-driven weather model capable of generating realistic ensemble forecasts at 2.5 kilometers across the Nordic region, while maintaining 31 km resolution globally. Built on a stretched grid architecture, this model focuses computational power exactly where it's needed, on the region of interest. But the real breakthrough isn't just the resolution. It's how the model learns to be spatially coherent at that scale. Traditional models trained with mean squared error, MSE, suffer from the double penalty problem. If a storm is predicted even slightly off its true location, the model is penalized twice, once for the false forecast, once for the missed event. This encourages smoothing, especially for extreme weather, the very phenomena we need to predict most. To fix this, Bris CRPS-FFT abandons MSE entirely. Instead, it's trained using the Continuous Rank Probability Score, CRPS, a proper scoring rule that rewards both reliability and sharpness. But here's the catch. A pure point-wise CRPS loss, even when applied at kilometer resolution, still produces spatially incoherent fields, noisy, fragmented, and physically implausible. The model learns the right values, but not the right structure. So we introduce a spectral component to the loss function. We compute the two-dimensional fast Fourier transform, FFT, of each forecast and target field, then apply CRPS to the Fourier coefficients. This forces the model to learn not just the correct mean and spread at each point, but also the correct spatial patterns across all scales, from large-scale pressure systems down to small-scale convective cells. This hybrid loss, point-wise CRPS in physical space, plus spectral CRPS in Fourier space, is what makes the difference. The result? Forecasts that aren't just accurate, but physically realistic. Sharp features like rain bands and gust fronts are preserved. Small-scale noise is suppressed. The power spectrum of the wind fields aligns closely with the reference NWP system, MEPS, especially for wavelengths longer than 10 kilometers. Now, let's compare it to the competition. We run Bris CRPS-FFT against Bris MSE, a deterministic model trained with mean squared error. Bris CRPS, a probabilistic model trained only with pointwise CRPS. MEPS, the operational Nordic ensemble prediction system. For 6-hour accumulated precipitation, the MSE model smooths out heavy rainfall into diffuse, featureless blobs, losing all distinction between isolated showers and widespread drizzle. The CRPS-only model captures localized events better, but introduces excessive high-frequency noise, like static on a radio, degrading spatial coherence. Bris CRPS-FFT. It strikes the perfect balance. It preserves the sharpness of real storms while suppressing unphysical noise. Zooming in on southern Norway, you can see the difference. MEPS shows well-organized convective bands. Bris MSE is blurred. Bris CRPS is cluttered. Bris CRPS-FFT is crisp, close to the true structure. We verify this quantitatively using quantal QQ plots. For precipitation, Bris CRPS-FFT underestimates the frequency of the largest events, but still outperforms MSE, proving that probabilistic training adds real value. For wind speed, it's even more striking. Despite being initialized from a single deterministic analysis, it produces a distribution closer to MEPS than the coarse resolution AFS CRPS model, a clear win for higher spatial resolution. And when we look at the power spectra using the discrete cosine transform, DCT, to avoid boundary artifacts, the story becomes crystal clear. Bris MSE lacks energy at small scales. Bris CRPS has too much high-frequency noise. Bris CRPS-FFT. It matches MEPS almost perfectly for large and mid-scale features, with only a slight excess at the finest scales, which we're actively working to correct. Now for the ultimate test, probabilistic skill. We generate 10 ensemble members for every forecast, compare them to MEPS's 30-member ensemble, and evaluate using fair CRPS, the gold standard for probabilistic forecasts. For 2-meter temperature, Bris CRPS-FFT beats MEPS, sometimes by up to 15%, because it doesn't lose analysis increments like the NWP system does. For wind speed, it's competitive. For precipitation, it's slightly worse at short lead times, but catches up and matches MEPS at longer ranges. Why? Because MEPS starts from an ensemble of perturbed initial states, capturing initial condition uncertainty. Bris CRPS-FFT starts from a single control analysis. This is a known limitation and a clear path forward. We also examine the spread-skill relationship. The ensemble spread should match the forecast error. Bris CRPS-FFT has less spread than MEPS, which makes sense, since it's trained on a single deterministic analysis. But its mean error is lower, meaning the ensemble is more accurate than it is spread out. This suggests the model is underdispersive, but highly skillful. Again, initializing from an ensemble of analyses could fix this. And for extreme events, we use the Breyer skill score. For precipitation, Bris CRPS-FFT performs slightly better than MEPS at high thresholds, a sign it's better at predicting rare, intense rainfall. For wind speed, it lags, possibly due to smaller ensemble size, or the lack of initial condition perturbations. So what does this mean in practice? Bris CRPS-FFT is now running operationally at Met Norway, 4 times a day. It's not just a research prototype. It's a real-time forecasting system, capable of generating high-resolution probabilistic guidance in seconds, not hours. And the implications are profound. Extreme weather, flash floods, windstorms, heat waves, is short-lived, localized, and sensitive to tiny initial errors. Conventional models struggle with these. But data-driven models, especially those with spatial coherence built into the loss function, can deliver the precise, reliable, and timely forecasts that national meteorological services need to issue life-saving warnings. This isn't just about better forecasts. It's about rethinking how we model the atmosphere. By combining graph neural networks, stretched grids, probabilistic training, and multi-scale loss functions, we've built a system that's not only faster than traditional NWP, but also more physically consistent and operationally viable. The future of weather prediction isn't just more data or bigger supercomputers. It's smarter models that learn not just what the weather will be, but how it will evolve with full awareness of uncertainty, scale, and structure. And with Bris CRPS-FFT, we're already there.